This is your class number 8 of module number 4 of your subject kinematics of machines. In the today's class, we are going to solve one problem on a roller type of a follower and which is having a cycloidal motion during outstroke as well as during return stroke. So you can see over here, so this is the displacement diagram for roller type of a follower in which the type of follower motion will be of cycloidal type. Okay, so for both outstroke and for return stroke, the type of follower motion is cycloidal motion. Already in the introduction class, we have seen there are four types of follower motion. One is with a uniform velocity, and one more with a simple harmonic motion, and one more is with a uniform acceleration and a retardation motion, and the last one is cycloidal motion. So this is the optimum motion of a follower in which the follower will be having a smooth movement. You can see over here there is no sudden rise or there is no sudden fall. Okay, the follower will be moving smoothly during a outward and during a return stroke. Okay, so that there will not be any vibration with respect to the follower movement. Let's get started with today's problem. So problem number 6. Okay, first I'll read out this problem. So this is the application type of a follower in which earlier I discussed cam and follower will be used to operate the inlet valve and the exhaust valve of a IC engine. Okay, the IC engine will be having a inlet port and the exhaust port. To control the opening and closing of those ports, a separate valve will be used. One is for inlet port, will be using the inlet valve, and to control the opening and closing of the exhaust port, will be using a exhaust valve. So these are operated with the help of a cam and follower. Okay, so these are operated with a cam. Okay, and you can see in this problem, the cam and follower is used to control the movement of the exhaust valve of a diesel engine. Okay, and it has a lift of 62.8 mm. It means whatever the valve that is used to control the opening and closing of exhaust port, okay, it is having a lift of 62.8 mm. It means the maximum distance that is covered, the maximum distance that is traveled by the exhaust valve is nothing but 62.8 mm. So this is nothing but the stroke length of the follower, that is S. And it is operated by cam to give a cycloidal motion during opening and closing periods. It means this valve, this exhaust valve, is again connected to a cam. Okay, and as the cam starts rotating, the follower means the exhaust valve, it will be opening and it will be closing. It means it will be moving up and it will be moving down. Okay, and with cycloidal motion, it is given whenever during opening time and the closing time of the exhaust port, the type of motion is cycloidal motion. It means I can consider opening means the outward stroke. It means the follower will be moving in a upward direction, and during the closing means the follower will be moving in a downward direction. That is nothing but a return stroke. It means both the outstroke and the return stroke is with a cycloidal motion, and it is given each of which corresponds to 120 degree of cam rotation. It means as the cam starts rotating from 0 to 120, the follower will be moving in a upward direction. Okay, it means the outward stroke is 120 and the downward stroke is also 120 degree. It means for the next 120 degree of cam rotation, the follower will be moving in a downward direction. So it is given each of which, it means the outward and the downward, it corresponds to 120 degree of cam rotation. It means theta naught is also 120, theta r is also 120. And the follower is provided with a roller of a 20 mm diameter. Since the roller diameter is given, it means the type of follower is a roller type. Okay, and the diameter is given as 20 mm. I want the radius of the roll, it will be 10 mm, and its line of stroke is radial. It means the follower axis is in line with the cam axis, so it is a type of radial follower. And one more parameter is given as the minimum radius of the cam is 25. Minimum radius is nothing but the base circle radius, so it is given as a 25. And draw the profile of the cam. Also determine the maximum velocity and acceleration of the follower during outward and the inward stroke. Inward is nothing but the return stroke. Both are correct. Both are same. And if the speed of the cam is 300 rpm in a clockwise direction, n is given, capital N, that is the speed of the cam in a clockwise direction is 300 rpm. So these are the given things, and as per this I'll note down the parameters. The type of follower is a roller follower, and it is a radial type. It means that axis of the follower and axis of the cam are in line. And stroke length is given as a 62.8 mm, which is mentioned as a lift. Lift is nothing but the distance that is traveled by the follower. The base cycle radius is given as a 25 mm, so I'll take it as a capital R. And one more parameter, the roller diameter is given, so it is a 20 mm. I want the radius, it will be small letter r is equal to 10 mm, which is nothing but the roller radius. And one more thing, as I discussed in problem number 3 and problem number 4, if the type of follower is a roller type, so you need to consider one more circle, that is a prime circle, which is a summation of a base cycle radius and a roller radius. So we can see the base cycle radius is 25, correct, and the roller radius is 10 mm, so the summation will be 35. So this comes only in case of a roller type of a follower. So the prime cycle radius will be 35 mm. And the speed of the cam is given as a 300 rpm in clockwise direction. And these are the four angles. So as I mentioned, the outstroke and the return stroke is with a 120 degree each. It is mentioned with a cycloidal motion. Both the outward and the return stroke is with a cycloidal motion. So nothing is given whether there is a dwell between the outward and the return stroke. So I can assume that, so the first dwell is 0, because nothing is mentioned about this parameter. Only they have mentioned the outward is 120, the return is 120. So I can assume that the dwell between the outward and the return stroke is 0. And the total the cam has to cover 360, right? 360. So already I have covered 120 plus 120, 240. So the remaining will be 120 degree. So you can see 360 minus the summation of theta naught, theta d1, theta r. So the remaining will be, I can consider as a second dwell angle. So you can decide as per the application part. So since nothing is mentioned about the first dwell, I can consider as a 0. Okay. So only they have mentioned the outward, that is a 120, the return is 120, and automatically the remaining will be the second dwell itself, because I need to cover total 360 of a cam rotation. So far I have covered only 120 and 120, 240, and the remaining will be considered as a second dwell angle. This is about angles and the given parameters. So this is a list of formula, and it is mentioned both the outward and the return stroke is with a cycloidal motion. So I need to consider these four formulas to calculate the maximum velocity during outstroke, maximum acceleration during outstroke, similarly for return stroke. So I can consider these four formulas. So first, I need to calculate the maximum velocity during outward stroke. So you can consider as a VE or V naught. Both are correct. So this is the formula. So you can see here 2 omega s by theta naught. Theta naught is the outward angle, that is a 120. To calculate this, I want omega. Omega is nothing but this angular velocity of the cam. You can calculate using this formula 2 pi n by 60, and is given as a 300 rpm. So I'll get omega as a 31.416 radian per second. A stands for ascent of the follower, or the outward motion of the follower. D stands for return stroke or descent. Means the follower will be moving in a downward direction. Okay. The VO or VA both are correct. VD or VR, that is also fine. After this, I'll substitute the value of omega, that is a 31.416 in this equation, so that I'll get VA as a 1.884 meter per second. If you substitute the value of stroke length S in the millimeter, you'll get the answer in millimeter. Okay. And if you substitute the value of S in meter, directly you can get this one. So you can follow any one, but finally I want the answer in meter per second. And one more thing is theta A or theta naught, it should be in radians, that is 120 into pi by 180. It is in degree, I'll convert into radian by multiplying pi by 180. So that maximum velocity during outward stroke will be 1.884 meter per second. Similarly, I can calculate the maximum velocity during a return stroke or the in stroke. Is the same formula. So you can see the formula is same, only the angle will be different. Theta D or theta R. Since the angle during the return stroke is also same, that is 120, I'll get the similar answer as of outward stroke. That is 1.884 meter per second. Because both the angles are same, 120 for outward, 120 for return stroke. Similarly, I can calculate the maximum acceleration during outstroke. Okay, so that is given here, 2 pi omega square s by theta a whole square or theta r whole square. Just substitute the value of omega s and this theta a or theta o, so that is 120. So this convert into radians by multiplying by pi by 180. So you'll get the answer in mm per second square because you have inputted the value of s in the millimeters. This convert into meter, it will be 88.782 meter per second square. Similarly, the maximum acceleration during the return stroke or the in stroke. So the formula is same again, only the angle is different. Theta A here and theta D. Theta D is nothing but theta R itself. Okay, D means a descent, R means a return stroke. Both are correct. Since both outstroke and return stroke are with the same angle, I'll get the similar answer because you can see the return stroke is angle is again 120. Okay, just consider this as okay, this is correct. Since both the outward stroke and the return stroke is with a angle of 120, I'll get the similar answer, that is 88.782 meter per second square, which is nothing but the maximum acceleration during return stroke. Okay, so these are the four answers. I got the maximum velocity during outward stroke, that is 1.884. Since the angle is same during the return stroke, I'll get the similar acceleration, that is 1.884. Similarly, it is the same case for acceleration also. During outward and during return stroke, I'll get the similar answer because the angle is same. Okay. After finding all these four values, I need to construct a displacement diagram which is required for drawing the cam profile. So you can see along the x-axis it is same. I'll take the angular displacement of the cam from 0 to 360. I'll plot the outward stroke, that is 120. Next, there is no dwell. I have assumed there is no dwell between outward and return, so I'll consider it as a 0. Immediately after this outstroke, I'll plot the return stroke, that is also 120. The remaining will be dwell. Okay, 360 minus 120 minus 120. So the remaining angle is also 120. So that is for the remaining dwell. So, and what about the construction of a displacement diagram during a outward stroke and during the return stroke? Okay, since the type of follower motion during outward and during the return stroke is a cycloidal motion, so there is a separate method which is known as a circle method. Since outward and return is both with a cycloidal motion, I'll draw a common circle. Okay, I'll use a common circle method so that I can save my time. So it is given the stroke length of the follower is a 62.8 mm. Okay, I'll explain how it is how to use a cycloidal motion or a circle method to draw the cam profile. To draw the displacement diagram. Okay, so first I'll indicate the x-axis, that is a cam rotation angle, and along y-axis I'll take a stroke length. I'll take the scale along the x-axis as 1 cm is equal to 20 degree. Along y-axis again 1 cm is equal to 1 cm stroke length. So first I'll indicate all the four angles, that is outstroke 120, first dwell 0, return stroke 120, and the second dwell is again 120. So 120 means 120 by 20. It means 6 centimeters. So before that, I'll indicate total angle itself from 0 to 360. So I'll draw one line like this. So 360 by 20, it will become 18 centimeters. And along the y-axis, I need to indicate the stroke length. So that is nothing but a 62.8 mm. I want in centimeter, it will be 6.28 centimeter. So this is a stroke length, that is S. After that, I'll divide this x-axis into outstroke, first well, return stroke, and the second well. So you can see the outstroke is with the 120 degree with the cycloidal motion. 120 by 20, it will become a 6 centimeter. And the first dwell angle I have assumed as a 0. So I'll not indicate anything because the angle is 0. And the return stroke, you can see it is a 120. So it means 120 by 20, again it will become 6 centimeter. And the remaining will be a second well angle. Okay, it means 360 minus 120 minus 120. The remaining angle is also 120 because total is 360. Total is 360. The remaining angle is 120 as I have noted in the given things. 120 means 120 by 20. Again, it will become 6 centimeters because the dwell angle is 120. So you can take the summation. Total, it will become 6 plus 6 plus 6. Total 18 centimeter. And after that, I'll confirm what is the type of follower motion during outward and during return. So it is clearly mentioned in the problem. Both outstroke and the return stroke is with a cycloidal motion. So I'll use a circle method. Since both the outward and the return stroke are with a cycloidal motion, I'll draw a common circle here. I'm using the circle method, and to save the time, I'll use a circle method at this point. I'll draw a common circle both for outward and both for return stroke. So before that, I need to divide the outstroke and the return stroke into 6 equal parts, correct? So since you can see the outstroke is with a 6 centimeter and I want 6 equal parts, 6 by 6 is 1 centimeter. So each division will be 1 centimeter, 1 centimeter. And I can give the naming from 0, 1, 2, 3, 4, 5, 6. And similarly, I'll divide this return stroke with a 6 centimeter into 6 equal parts. Again, it will be 1 centimeter each. So since there is no dwell, so I can continue from here. The sixth line will be common to both outstroke and the return stroke. It means 6, 5, 4, 3, 2, 1, 0. I'll not divide about this one. I'll not divide this dwell angle. Only I'll divide the outstroke and the return stroke. As I said, both the outstroke and the return stroke are with a cycloidal motion. I'll use a circle method and it will be common to both. Okay. So at this point, before drawing the circle method, I'll take the reference points. So I need to start from here. So this is the first reference point. I need to end here. So this is the second reference point. Again, I need to come down. So because the follower will be rising for 120, again it is coming down for next 120. Again it is a dwell. This is the first reference, second, third. So you can give any namings. So I can consider this as a O1, O2, O3. You can consider any points, any namings is okay. So at this reference point O1, I'll draw a circle. Okay, so this is the pink color circle. And as I explained in the introduction class about the cycloidal motion, you need to construct a circle in such a way that the circumference of this circle is equal to the stroke length of the follower. So what is the circumference of the circle? It will be 2 pi r. Okay, and this is the stroke length. It means S is equal to 2 pi r. It means the circumference of this circle will be equal to the stroke length of the follower. S is equal to 2 pi r. I need the radius, so radius becomes S by 2 pi. So you can see it is the same thing. R is equal to S by 2 pi. So if you want a detailed explanation, you can go with the introduction video so that you'll get the radius of the circle as S by 2 pi. I know the value of S, that is a 62.8, and 2 pi, I'll get approximately 10 mm. 10 mm means 1 centimeter. Just construct the circle with a 1 centimeter radius at this point. And after that, I need to divide this circle into 6 equal parts. So first I'll take this as a reference point, point 1, and with the radius of 1 centimeter, I'll draw one arc here. I'll use a compass. I'll take this as a reference, and just take the radius as 1 centimeter. Just draw one arc here above and one arc below. It will intersect the circle at 2 points. I can consider as a point 2 and point 3. The similar manner, just take this as a reference point. Again, take the radius as 1 centimeter. Just draw one more arc here and one more arc here by taking this as a reference point. It will intersect the circle at these 2 points. So I can give the naming as a 5 and 6. It means I got 6 equal parts. I have divided this circle into 6 equal parts. And after that, I'll join 2 to 5, and I'll join 1 to 4 and 3 to 6. Now I got 3 horizontal lines joining 2 to 5, 1 to 4 and 3 to 6. And you can see here, this horizontal line joining 2 to 5, it will intersect this vertical line. You can see the vertical diameter of the circle at this point. You can zoom this area. So this horizontal line, it will intersect this vertical diameter of the circle at this point. So this is the intersection point. In a similar manner, this horizontal line, that is 1 to 4, it will intersect same diameter, same vertical diameter at this point. This is also one more intersection point. And this 3 to 6 horizontal line, it will again intersect this vertical diameter of the circle at this point. So these are the 3 intersection points. So I can give the naming as A, B, C. So you can see, so these are the intersection between these 3 horizontal lines with respect to the vertical diameter of the circle at point A, point B, point C. And after this, and this circle is common to both outstroke and return stroke, because both outward and return stroke is with cycloidal motion. After that, I'll take a reference as O1. I'll join O1 to O2 like this. Okay. You can see O1 and B are at this point only. So I'll join O1 to O2 like this. And after that, from point A, I'll draw one line which is parallel to this previous line. You can consider as a BO2 also, because at this point, both the points B also comes, O1 also comes. So I'll explain once again. So from this point, now I got these 3 reference points, that is A, B, C. From these 3 reference lines, I'll draw the diagonals or inclined lines such that first from this point B, I'll join O2. So it's like a diagonal in a downward direction. And similarly from point A, I'll draw one more line such that it will be parallel to this previous line, that is BO2. You can see draw a line from point A which should be parallel to BO2. The similar manner from the third intersection point, that is C, I'll draw one more line which is again parallel to this BO2 like this. You can see this is also parallel to this BO2. This BO2 is a diagonal, and so you can see these whatever the line that is coming from A and whatever that is coming from point C, so both are parallel to this BO2. So you can draw a line from point C which should be parallel to BO2. Similarly, towards my right also, I'll draw a diagonal like this, so which is joining again from B to O3. Again from point A, I'll draw one more line which is parallel to this BO3. So again from the same reference point A, B, C, I'll draw one more line which should be parallel to this BO3. The remaining is this third intersection point, that is point C. Again from this point C, I'll draw one more inclined line which should be parallel to BO3. You can see draw a line from point C which should be parallel to BO3. And after this, I need to indicate the intersection between these inclined lines with respect to the vertical lines, that is 0, 1, 2, 3, 4, 5, 6. So since you can see, so this is a 0 value of the stroke length, and this is the outstroke, it means the curve has to be moving in an upward direction. So there is a rising of the follower. The curve will be like this. After that, it will come down like this. It means this is the first inclined line, correct? This is the second inclined line. This is third inclined line with respect to the outstroke, because the curve is moving in upward direction. First, I'll consider this as a first inclined line. So this inclined line, which is coming from point A, it will intersect the first vertical line and the second vertical line. So you can see here, this is the first vertical and second vertical line. This is the first inclined line, which is coming from point A. It will intersect the first vertical line and the second vertical line at this point. So if you want, you can zoom this area. So this is the first intersection point and the second intersection point with respect to the vertical lines and this inclined line, the first inclined line. So I can name it as 1 dash, 2 dash, and you can see the second intersection point or the second intersection, second inclined line. Sorry, so this is a second inclined line which is coming from point B. It will intersect the third vertical line at this point. This will be 3 dash. Similarly, so this is a third inclined line which is intersecting the remaining two lines. That is a fourth vertical line and fifth vertical line. It will be 4 dash and 5 dash. So if you want, I can show the intersection points. You can see this is the first one, and after this, this is a first inclined line which is coming from point A. It is intersecting the first line at this point, so it will be 1 dash. This will be 1 dash, and the same line, it is also intersecting the second vertical line at this point. It will be 2 dash. And you can see the second inclined line which is coming from point B. It is intersecting the third vertical line at this point. So this intersection point is 3 dash. And the remaining two lines, that is the fourth and fifth vertical line, they'll intersect with the third inclined line which is coming from point C at 4 dash and 5 dash. And the last one will be 6 dash. The similar manner, just follow same method whatever you use for the outstroke for this return stroke also. Now the curve will be coming down like this. So I can consider this as the first inclined line, second inclined line, the third inclined line. So again, I'll use the same method. So whatever the line that is coming from point C, that is the first inclined line, it will intersect fifth line and the fourth line at this point. If you want, you can zoom this area. So this is the first inclined line which is coming from point C. It will intersect the fifth line and the fourth line at this point and at this point. So I can name it as 5 dash and 4 dash. In the similar manner, whatever the line that is coming from the second inclined line, that is from B, it will intersect the third vertical line at this point. It will be 3 dash. And this is a third inclined line which is coming from point A. It will intersect the remaining two vertical lines, that is second vertical line at 2 dash, the first vertical line at 1 dash. So in this manner, I got 6 points, that is 1 dash, 2 dash, 3 dash, 4 dash, 5 dash, and 6 dash with respect to outstroke, and again same for return stroke. So 6 dash will be common for both outstroke and return stroke because there is no dwell between the outward angle and the return angle. And after that, after getting all these points, I'll draw a smooth curve just to pass through all these 12 points. That is from 0 to 1 dash, 2 dash, 3 dash, 4 dash. I'll draw a smooth line. You can see the red color line. So it is for first outstroke and this for a return stroke. So you can see, you can observe with all the remaining type of follower motion, the curve is rising smoothly and it is coming down smoothly. So there is no sudden rise, there is no sudden fall. That's why this is a most used type of a motion, that is a cyclodal motion, for both applications of aerospace and automobile industry to control the motion of an inlet and exhaust valve of an engine. Because I want a smooth movement of a follower without any vibration, so I can select this type of a smooth curve, which is nothing but a cyclodal motion. And you can continue this, you can extend this curve because there's a dwell for next 120. It means there's a zero displacement of the follower. So you can draw a red color straight line. It is not indicated, just draw it. So this is a circle method which is used for a cycloidal motion. Okay, I'm drawing only single circle because to save the time, the outward and the return stroke both with the cycloidal. So I'll draw a common circle and I'll draw the inclined lines towards my left and right. Okay, and after drawing this displacement diagram, I'll go to the cam profile, and it is in the problem it is mentioned the type of follower is a radial follower with a roller as a follower. Okay, type of follower is a roller, and it is also called as a radial because the axis of the follower and the axis of a cam are in the same line. Okay, so this comes under a category of a radial follower. Okay, and only in the problem number 3 and problem number 4 I explained how to draw the cam profile, and the type of follower is a roller type. Okay, you can follow the same method. So first you can indicate the center of the circle. You can take this as a point O. So first you can draw the base circle. You can see this is a base circle, so with a radius of 25 mm or 2.5 centimeter. After that you can indicate the prime circle. So this is a prime circle with a radius of 3.5 centimeter or 35 mm. So I already explained why this prime circle comes only for a roller type of a follower. In the case of problem number 3 and problem number 4, you can follow the same methods. And after drawing this, I'll indicate the follower. At this point I'll indicate the follower axis and the cam axis in the same line. Okay, and I'll take the reference as prime circle. Again, as I explained in the previous class, again I'll take the reference line. The axis of the follower, which is passing through the center of the circle, it will intersect the prime circle at this point. So I can consider this as a point A, and at this point I can indicate a roller, and it is given the roller diameter is 20. It means the radius will be 10 mm or 1 centimeter. By taking the center of a roller as point A, I'll draw a circle with a radius of 1 centimeter or 10 mm. Then I'll indicate the follower with some height. After that, I'll join point O and point A, and it will be the first reference line. That is, OA is a reference line. And use the protractor and start indicating the angles in the counterclockwise direction because the cam is rotating in a clockwise direction. It is given in the problem. The cam is rotating in a clockwise direction, so I need to indicate all the angles in the counterclockwise. By taking the reference as OA, and A should be on the prime circle only. Just ignore this base circle in the case of a roller follower. Okay, so first I'll indicate the first outward angle, that is a 120. Okay, it means AOB, it will be 120. AOB, it will be 120. And for the next 120 there will be written stroke. It means a BOC. This is a BOC. Okay, this will be 120 on the prime circle only. You need to locate point A, point B, point C on the prime circle only. The remaining will be dwell, that is 120. That is COA. These are the only 3 angles I need to indicate with respect to the prime circle. Again, use the same method. I'll divide AOB. I'll divide the prime circle between this AOB into 6 equal parts. Since the total angle is 120, I want 6 equal parts. That is 120 by 6. That is a 20 degree. So I'll indicate 1, 2, 3, 4, 5, 6. Such a way that each division will be 20 each with respect to the prime circle only. Okay, between only A and B. I got 6 points. In the similar manner, I'll divide this written stroke also, that is a BOC, into 6 equal parts with respect to the prime circle between point B and point C. That is a 6, 5, 4, 3, 2, 1, 0. Here the sixth point will be common to both outward and written stroke because that well is 0. Again, after dividing the outward and the return stroke into 6 equal parts, from these reference points on the prime circle, that is 1, 2, 3, 4, 5, 6, draw the radial lines towards the center of the circle from point 1, from point 2, 3, 4, 5, 6. Similarly for return stroke, that is 5, 4, 3, 2, 1. Okay, I'll get the radial lines like this from point 1 to point 6, and from point 6 to point 1. Towards the center of the circle, I got radial lines. And just extend those radial lines in a backward direction like this. So from point 1, 2, 3, 4, 5, 6, again 5, 4, 3, 2, 1, 0 with some convenient distance. Use the same methods whatever I explained in the previous class for a roller type of a follower. After that, just transfer the displacement distances from the displacement diagram. 1 to 1 dash, 2 to 2 dash. Just wait for a second. After this, as I said, from the displacement diagram, I need to transfer the distances, that is 1 to 1 dash, 2 to 2 dash, 3 to 3 dash on these radial lines, both for outward and both for return stroke. You can get here, this is a 1 to 1 dash, 2 to 2 dash, 3 to 3 dash, up to 6 to 6 dash for outstroke. In a similar manner, 5 to 5 dash, 4 to 4 dash, up to 1 to 1 dash. Just copy these vertical distance with the help of a compass and transfer over this cam profile by taking the reference as 1, 2, 3, 4, 5, 6, 5, 4, 3, 2, 1, 0 on the prime circle. And just transfer those distances on these radial lines from 1, 2, 3, 4, 5, 6. You'll get 1 dash, 2 dash, 3 dash, 4 dash, 5 dash, 6 dash up to this one, the last circle. Okay. After getting all these points, just take those points as the center of the circle. Just indicate the rollers. The radius of 1 centimeter, 1 centimeter, 1 centimeter. The center will be 1 dash, 2 dash, 3 dash, up to again this point. After getting all these rollers, from the first roller, just start drawing a curve such a way that it will be tangent to all the circles. It will be tangent to all the circles and end here. And you have started here. Again, just complete this cam profile around this base circle. Okay, so this will be your cam profile for the cycloidal motion. Okay, and you can follow these steps. So whatever I explained, the problem number 3 and 4. Okay, just take these steps and take this as assignment. Okay, try to complete this cam profile for the cycloidal motion as well as a roller type of follower. Okay, already got the displacement diagram by using this cycloidal motion, and there is no separate method for a cycloidal motion to draw this cam profile. The same for whatever you used for a roller type of follower. There is no separate method for this cycloidal motion. Only the method will different for drawing this displacement diagram. Only I want these vertical distances. Okay, the remaining steps are same to draw this cam profile. Okay, so please take this as assignment. You can take these steps and try to complete. Okay, so if there is no doubt in this cam profile and displacement diagram, okay. And one more thing is, so in the notes I mentioned clearly what are the different types of follower motion, that is uniform velocity, this UA, RM, SHM, and this cycloidal motion. And I have not solved any problem on this first case because it is easy. You can get in the RS Cormi textbook. Okay, it is the easiest method. Okay, so directly after dividing this outward and the return stroke, directly you can draw the diagonals like this and one more diagonal like this. So this diagonal AB will intersect the vertical lines directly at 1 dash, 2 dash, 3 dash, 4 dash, 5 dash. In a similar manner, you'll get the reference point. Okay, so this is a simple method. That's why I not solve any problems on this uniform velocity. If in the examination it comes the follower with the uniform velocity, you can use this method. You directly can draw the diagonals and you'll get the intersection points. Okay, And I have solved problems on this second type of a follower motion, that is a uniform acceleration and the retardation motion. So this is also very much easy. I explained in the previous class. So these are the steps you can go through, and I covered the problems on this simple harmonic motion, the follower with a simple harmonic motion using a semicircle method, both for outward and a written stroke. And you can go through these steps. And in the today's class, I have covered the follower motion with the cycloidal motion. Okay. If there is a dwell in between the outward and the written stroke, you can use a separate circle for outward and for the separate circle for written stroke. The today's problem, since there is no dwell at all, there is a continuation from outward and a written stroke, I have used a common circle to save the time. Again, the method will be same. Instead of drawing the circle here, you can draw the circle here. And these are the steps you can go through. And as I explained, for high speeds, the cycloidal curve is best, okay, to design the surface of the cam profile, so that you can reduce the vibration, can reduce the wear, stress, and noise. Okay, that's why for most of the application we'll go with the cycloidal motion, and in which the circumference of the circle, that is a 2 pi r, it will be equal to the stroke length of the follower. It means the outer periphery, the total circumference of the circle will be equal to the stroke length of the follower, that is s is equal to 2 pi r, so that r becomes s by 2 pi. Okay, so these are the steps you can go through, and from the RS Cormi textbook you can try some more problems so that you'll get more confidence. Okay, so you can take this as assignment, this cam profile, drawing the cam profile as assignment, and just go through these steps, you'll get the answer. Okay, so if it is clear, I'll wind up today's class. Okay, thank you.